Now, so back to where we left off. We covered diffusion rather thoroughly. I wanted to get into a little bit more detail about what we call facilitated diffusion. All it means is there are carrier channels that are for, and this is a typo, hydrophilic molecules, because glucose, amino acids, and ions, okay, like water, they're hydrophilic, but that's the nature of these things. And they get into a distinction between carriers and channels. Effectively, channels theoretically are always open, and carriers imply that there is some structural change or something that it really truly allows uh, something to pass in and out, as you will see. But I don't want to get into that for the time being now. Okay, so I mean, you'll see that there's typically carriers mean there's some type of protein that has a shape change, and a channel means effectively, and it varies by the number of channels and the size of those channels and how they're constructed is what can get through. But it's basically, it's water, small molecules, particularly as you will see today. This is a really important day, and I'm glad that, and thankfully, the classes by and large are showing up, and I'm very thankful for that. I mean, I have trouble first thing in the morning having to listen to me all. My wife goes in the other room. So carriers, transmembrane, integral proteins, basically just in allowing stuff to get in and out that are there, very, very specific. Because sodium gets through one, potassium won't get through the same one necessarily. Okay, most of the time they're very, very specific. Some work in both ways. Okay, and effectively, sometimes something will just the very act of proximity of that molecule will change the shape and allow things to go in. And they talk about saturated, and doesn't play a big role in what we're studying now, but you have a limited number of these carriers. When they're all occupied, effectively nothing else can get in. But I think it's a different concept for a different time. And they show you some interesting illustrations that are there. This is sort of the shape change deal. So here's like a sugar coming in contact or close proximity. It'll change, like I said, things will change the shape of the protein. It'll allow it to be pushed in, and the shape change on the other end will allow it to enter the interior of the cell. Channels effectively transmembrane, water-filled cores, and transport ions such as ions, and you're going to see very, very shortly about sodium and potassium being really important players, and water certainly is part of it as well. Specificity based on the pore size or the charge. When we talk about pores, typically that's short for aquapores. Nearly all cells have these to some extent. Okay, and so it would be almost unheard of not to have a cell being there. So it's highly unusual for water not have the freedom to move in and out. Typically, when we talked about those tight junctions previously, okay, that's really tight junctions are about cell to cell connections. So if there's any movement of water, it's between the cells, not necessarily through them. So don't be confused about that. And really, this is something that's going to be the crux of what we're going to talk about endlessly when it comes to nerve and muscles: leakage channels and gated channels. Leakage channels always open. The number of those channels will play a pivotal role in something that we're going to look at today called the resting membrane potential. Gated channels are something that you'll hear about. You're sick and tired of it. You're going to hear about chemically gated, which in another term you'll see we use a lot in these animations and in the presentations. Ligand gated channels. That's really significant of the signaling that goes on, how nerves talk to other nerves, how nerves trigger muscles to work, and then something called voltage gated channels. So those are all coming. That's why the foundation is so important, so you understand what I'm referring to. So typically, here's a channel, whatever goes through here. Which brings us to this, because we're talking about water. The whole idea, we get so confused with your sodium, your potassium, your sugar. We don't think very, very well about You really don't think about the relationship consistently of solute to solvent. This is really, water is our solvent. So water is no different than anything, whether it's sodium, potassium, glucose, dissolved in water. Water moves too. Water has its own concentration. So without going crazy about what it is, you had two identical containers volume-wise, and you had 9 different things in one and 3 different things in the other. So effectively, you'd have here, you'd have a 9 to 1, 9 particles, so to speak, for one container. Here you have 3 particles. So the particles are solutes. And understand, when you put a sodium, it ionizes into sodium plus Cl minus. So 1 unit of sodium chloride is for 2 particles. 1 unit of glucose, although it's considerably bigger, 1 particle. And so on. So when we look at the relationship, particularly with regard to osmosis, we are looking at the number of particles, not bigger, smaller, rounder, squarer. All about number of particles. Together, that plays a very important role that we're going to get to, called osmolarity. And the normal in our bodies is this, 300 milliosmoles. It means, and without going into it includes everything that's dissolved in the water that constitute a particle, all different kinds of chemicals, sugars, salts, etc., etc. And that's a really important number down the road for us, for you to look at. But for the time being, we have these 2 containers. So obviously, this has a higher concentration of solutes, 9 to 1 to 3 to 1. But this one, just looking at it, has a lot more space, needs a lot more water. So if you flip the fraction, 1 unit of water with 9 things in it, 1 unit of water with 3 things in it. I know where you come from. Where I come from, 1/3 is always bigger than 1/9. Okay? That's the way you can look at it if that works for you. And what that means, as you'll see in some of the illustrations, that if water had the capability of moving, it would push into this. And if possible, change the volume. Water has a movement of water has a force, and a powerful force of its own. And we'll get back to those osmolarities and things like that in the context of what that means biologically. The whole idea of using something called normal saline, 0.9%. 0.9 grams of salt, regular salt, dissolved in 100 milliliters of water. Years ago, and remember, there's 2 particles, and you have to do the molecular weight, and you have to do the chemistry and how many moles. We're going to do that. Good. That's after us, chemistry. Yeah, you. I'm very grateful. Very offbeat. D5W is dextrose. Much bigger molecule, 5%. 5 grams of dextrose in 100 milliliters of water, yet it has the same number of, basically these both end up with that 300 milliosmoles. And what you're going to see with the burn patients who have to do fluid electrolyte balances, we use something called lactated ringers. Yes, it's the same. You'll see down the road that all of these are isotonic. That means they all have 300 milliosmoles, and that's what we have in the intracellular fluid, extracellular fluid. Water plays is different. Crazy with this, it's so terribly important. It's why if somebody is underhydrated or overhydrated, they are in peril. They can kill them. And I forgot to tell you, I told my Wednesday group this story. It's an absolutely true story. When those Wii systems came out, the computer game systems, this is an LA area, some radio talk show host. I'm going to have a contest with the name Wii down in P. He said, we'll have 2 contestants. They're both going to have to drink water, and whoever can hold on to the most water is going to win a Wii system for their kid. And this lady won. Fortunately, she died like a day or so later. Because she was overhydrated. Absolutely true. You can look it up. I mean, a number of years ago. So I've been using that anecdote for a long time. It's crazy. So don't think anything is innocent like that. It's not. I mean, most of us, if you're working out, if you feel like you're dehydrated, you drink a bunch of water. You don't overhydrate yourself. You're just replenishing it. You kind of know when to stop. That's there. So when we talk about the movement of solvent, water, not molecules, across the selectively permeable, normally everything's in equilibrium because water can move and the solutes can move. And equilibrium just means that once they reach what we call a steady state, you'll have the right numbers on each side, and every so often a water will move here, a particle will move here, and they move back because everything is in motion all the time. The only time it's not in motion is if you're deceased. Then things stop moving. So as long as you're alive, things are moving all the time. So here it is. Water is polar, but it's so small it can squeak or sort of like squeak through or squeeze through. Aquaporins are there, blah, 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 blah. Here it is. They're just showing it to you. Osmolarity, don't go into the definitions. It's all about the number of particles we call solutes. Okay, varies with the number. It's not so much the size of the particles, but the particles themselves they're all relatively small, and they displace a certain amount of water that's there. And that's where you get the science behind it. So water moves by osmosis, just like anything else, from high water or low solute, that's the confusing part, low water or high solute concentrations. Just think about the way I've expressed it there. The more stuff in the water, proportionally speaking, you have less water concentration. So they're separated by a membrane that everything can cross to reach equilibrium. And things always move. And they show you this. So if magically we could flip a switch and open that doorway so the particles could move and the water could move, they would balance each other out. That's typically what we see. Typically what we see. So we don't push too much water in or pull too much water out. Osmosis, different because we're just looking specifically at the water. Water will have a net movement across the membrane until it has the same water concentration on both sides. So if it's a membrane that's permeable only to water, the solutes can't move. Okay? Low solute side volume decreases, high solute side volume increases. Better to show it to you. Here's the magic doorway. More water available here, concentration-wise, because you only have a handful of particles. Here you have at least twice as many particles. Flip the switch. Look what happens. I've done this in lab many times. They're called osmometers. You have all sorts of different ways that you can do this. Okay, demonstrating how the water, and you can actually watch the level change. Do it at the start of the lab, and at the end of the lab, you'll be able to see it. But what effectively happens, it alters the volume. And the whole idea, okay, where this can cause problems is because our cells are different. Okay, our cells aren't like plant cells. That's where that overhydration comes in. I mean, particularly probably not this morning after raining overnight, but I mean, if you have plants outside, like we have our deck has plants everywhere, like that, and my wife's very conscientious about watering those things. If the plants get a little droopy, what do? We water it. And when it's watered, the plant goes, water. I'm so happy. Brightens up, perks up, hi. Like that. That's a happy plant. It's a watered plant. Hard to overwater them. And why is that? Plants have cell walls. So it pushes against the cell wall, and it actually causes that almost change in the shape or the position. By the same token, if it doesn't have enough water, the cell walls are basically starting to pull in on one another, if you want to think of it. It really has to do with the material. That's how, if you did not know, bacteria have cell walls. That's why you'll find in bacteria that adding water to that area mechanically, we could wash that away. That's useful, but it's not going to destroy them. Bacteria, very much with the exception of a couple, don't like things that have a lot of salt with regard to them because it pulls water out. That's what really damages. It's like putting salt water on your plants. It sucks the water out of them and they collapse on the interior. The walls stay intact, but the cellular contents become damaged, and eventually the plant or the bacteria dies. So the earliest days, and I talk about this in micro, how we preserve foods was salting. We didn't have refrigeration, obviously. Ice was very difficult to acquire unless you lived in close proximity, and they knew coal would at least retard that. So what they did back in the day, if you didn't know the derivation of it, the Roman soldiers were paid in salt. Some gold too, obviously, but salt. Okay? That's the derivation of the word salary. And they would use that salt around meats and around vegetables, suck the water out of them. Bacteria couldn't cause it to spoil. All we had to do was wash it off. You can go back and fancy cooking. If you go in Italy, some of those traditions are there. If you buy a thing called bacala, which is salted cod, okay, it comes that way. That's the best kind. And you have to rinse off the salt and put it in milk and rinse off the salt. It's a delicacy. So it has a lot of applications in that. And so that was the old saying. If they said if someone is not worth their salt, they weren't doing their job as a soldier. And they got sent to the salt mines. See, a little history helps you understand anatomy and physiology. I know, I always use that stupid thing. Okay. By this time, my wife would be throwing things at me. Say the same stupid stories all the time. So, the whole idea of this has to do with pressure of water, pushing in and pulling out. Hydrostatic pressure, your blood pressure. It's hydrostatic. It's the force of the water. It's not just pushing fluid along away from the heart or back toward the heart. It's pushing against the walls of the blood vessel in all directions. I mean, a blood vessel, so the force also goes against the walls. When we do blood pressure, you put enough pressure to collapse them. As you start to release that pressure, eventually it reaches a point where it can push back and expand it, and we get a pulse. We call that the systolic, that first sound that you hear. That's the whole idea of taking blood pressure. Hydrostatic pressure. That would, at the capillaries, they're permeable. Stuff can sneak out. And what happens is what opposes that is called osmotic pressure. The proteins and all those other elements exert a pull. We talked about it before. A colloid, the proteins exert a pull, as well as the other elements that are dissolved in the water, and they hold the water in. When we get down to the capillary levels, when you study that in blood vessels in AP2, that's why when you enter the capillary, stuff comes out, and when you get to the end of the capillary and start to form a vein, we pull stuff back in, waste products, fluids, etc. It's just the way it's elegantly designed anatomically based on different kinds of pressures and what's still in the blood vessels. So that's what happened. So the big problem is this. Plant cells, again, limit that pressure from causing a problem. Plant cells will fill only so much, the water will stop. They also have, you remember your plants, if you remember in high school bio, they have vacuoles, they pump out the extra water. We don't have those. Animal cells don't have it. They cannot tolerate it in either direction. Too much or too little. Okay, so it will shrink, and that's really where the problem is with hydration. With people who are overly hydrated, but particularly dehydrated is much more frequent, and the people who have the less ability to tolerate that, they're very old and they're very young. That's why you worry about that when they get vomiting and diarrhea. It's a big deal to make sure somebody's well hydrated. And these are the fancy names. So the ability of the solution to change the shape or the tone of the cell. That's where the term tonicity comes from. Tonicity is really relevant or related to the relationship between solutes and solvent. So, and if you want to think of like muscle tone, okay, isotonic, the same osmolarity inside the cell, and that's what normal saline and D5W and lactated ringers. We very, very rarely put something in. When we use an IV, we'll add stuff to the IV, but the main fluid, there's some very limited application. If someone's overly hydrated or dehydrated, where you might change it. That's something for those who go into clinical fields, you'll learn about. But when many of you will be starting IVs, will start an IV, it'll be normal saline, and you put whatever you have to put in. Hypertonic, think salt water. sucks the fluid out. It undergoes a process called crenation. Basically, it begins to shrivel and become irregular. And hypotonic, the cell lyses. The fancy name we use for it is called plasmolysis. As you can see there, it's the osmolarity here. I used to do this experiment when I do like a phys lab. We get some aseptic blood that can't harm anybody, and effectively you put a teeny tiny amount, and first you put it in normal saline. Okay, and you look under the microscope and compare it to what normal blood looks like. Doesn't change at all because water's neither moving in or moving out. If you put it in 3 to 5%, that's roughly what salt water is from the ocean. And immediately, this is electron microscopically, in light microscopy, it starts to almost like square off. You get almost pointed edges that are there. That's a dysfunctional red blood cell. That's what crenation is, shriveling. And now, I am super fast at focusing a microscope. Now, I try to focus it as fast as I add it to like the triple distilled water, so effectively water without any electrolytes in it. I can't even see this. All the cells have burst by the time I focus it. And I can do it in seconds. I got my first microscope when I was 6. It's true. Nerd, inner nerd. You know why that? Because my parents, so I did what I did with the chemistry set. They said, there goes the chemistry set, Lou. The kitchen will never be the same. Microscope is less work. It's true. I was that kid. Keep them busy doing something. It's driving us crazy. And ladies and gentlemen, that concludes passive transport. A lot of activity for passive transport. But no, we're not done yet. In the remaining half of our presentation today, we're going to start to look at active transport. And active transport is terribly, terribly important. And so this is the next one of these, and you're going to see the really good animation that we're going to get to very, very shortly, dealing with something called resting membrane potential. So active transport, there are 2 types. Active transport classically involves using ATP basically to move stuff in and out of the cell. When we do bulk movement, and we're not going to probably get to that today, basically we're trying to latch onto something and pull it into the cell. We open the membrane, change its shape, and latch onto it. Okay, or if we have something in the cell we want to get rid of, we have a membrane around it to protect it, and we spit it out. Effectively, that's what those 2 types of transport are about. So vesicular transport involves opening and closing membranes. Even though the membranes have the ability to do that, it requires a certain amount of energy to get this accomplished. We'll probably just touch on this in the beginning. But active transport is something that we spend a tremendous amount of our energy resources on. And you see, we're very frugal with energy resources. If we have to spend an ATP, we want to be able to accomplish a lot with it. Moving a lot of stuff in or out would be one way, but class of active transport, okay, is what you're going to see first. So in this case, why do we have to use it? It's too big for the channels. It can't get through the membrane, or we're going against the concentration gradient. And so what happens, we call the term pumps. See the term pump, and you're going to talk very shortly about the most famous pump of all, sodium-potassium pump. Every single cell has these. They are extraordinarily active in nerve and muscle cells. In the rest of your cells, they're active only rarely, comparatively speaking. But yes, take that all into account. Nearly half of your energy expenditure every day is to maintain something called the resting membrane potential through these sodium-potassium pumps you will see shortly. So how do we spend our energy? Carefully. So antiporters and symporters. So if we're bringing something in, if we've opened a channel passageway and we're bringing something in, we're going to use that same energy to push something out. So things will go in 2 directions, typically through different channels, sometimes the same channel. Okay. Sometimes it's almost like we're in a swimming pool in a race, and they draft, or in a race car race. We'll bring something in, and we'll use that flow to bring other stuff in. That's really a way that we retain glucose in our bloodstream rather than expelling it in the urine, and you'll see that in the kidney. That's called sim-porting, meaning, or co-transporting is probably a better way to express it. And authors both use those terminologies. So when we're moving something against the concentration gradient, okay, this is how we accomplish that task. That's there. So when we're doing the energy directly from ATP, that is called primary active transport. The secondary is that sim-porting and anti-porting, moving things using that energy through opening multiple channels or involving additional things going along with it. That's the distinction between primary active transport. For the time being, just think about ATP and active transport. In my advanced physiology class, when we do this in the spring, we get more involved in the distinction between primary and secondary. That is there. This is the big player. It's the hydrolysis of the ATP, basically releasing that high energy bond, causes a change in shape in that transport protein, and effectively we can move charged particles particularly. And you'll see this when we get to digestive. If you get to that in AP2, you'll talk about proton pumps, so important with acidity in your stomach. And then this one, the sodium potassium pump, the big player. Most studied, fancy name, sodium potassium ATPase, which means effectively it's an enzyme. It breaks apart the ATP, and we use that energy to move sodium potassium. Interestingly, they're using the same passage, which you will see shortly. So all plasma membranes, especially active in excitable cells. And really, this is the framework for you to understand early on what's going on in nerves and muscles. Because every student who I've ever taught in this course over the, I don't know, 25 years I've been doing it, that's the hardest thing to understand. Nerve and muscle physiology. Voila. We'll go through that. We'll come back and look at these. Do the animation first. This is called the resting membrane potential. You will see very shortly. Pick these things up off the floor. As you'll see very shortly. Every cell, whether it's a nerve or muscle cell or just a garden variety, basically when you get to its membrane outside the cell, it always has more sodium. So what happens is, right along that membrane, positively charged, inside the cell always has more potassium. But as you will see, the inside of the cell, negative. That's a lot to do with proteins. So, across that cell membrane, every living membrane has what we call polarity. Positive right along the membrane, and they even measure this, you will see shortly, something called minus 70 millivolts. No idea how small that is. But this is the resting membrane potential animation.
The human brain alone contains about 100 billion nerve cells, called neurons. A neuron, like every other cell, has positively and negatively charged ions, inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of minus 70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allows sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at minus 90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to minus 70 millivolts.
Here it
Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks. Thus, the pumps help to maintain the resting membrane potential.
So a couple of things that are worth noting with all of that. You can look at this as many times as you wish. It is so important because you're going to begin to see the role that this plays in conducting impulses along muscles and nerves, how it works with directionality. Is there directionality or not? Does it go randomly or does it go in a specific order? All of that is based on this resting membrane potential. And you're going to see things that cause this to determine whether or not a nerve will fire or whether a muscle will fire. We build on this constantly. And so it really underscores particularly the importance of sodium. I've said it before, clinicians, doctors, nurses, people who work and study blood tests, when they see sodium levels drop or sodium levels get high, it is a big, big problem because that's the critical piece. And why? Because you have more of those leak channels. That's a leak channel. It's always open, but because of the greater number of sodium leak channels, sodium is the key player in resting membrane potentials. We have a very, very wide range of sodium that when you look at a laboratory test, you have a very narrow range for potassium, a very, very narrow range for calcium. So you can understand that's where the importance is. So calcium and potassium are big time players. Just wait till you start to look down the road at how the heart works and all the different kinds of ways how the heart muscle contracts. They are so terribly important. So I urge you to understand this is really, and it's not something for this exam we're coming up now. It's going to come up in the future. The other thing that's relevant about that is this. If you look at those sodium potassium pumps here that they're showing you, it's a 3-to-2 relationship. For every 3 sodiums that it pumps back out, 2 potassiums are brought back in. That's a very consistent relationship to get used to. Sometimes in this case, it's through the same passageway. Sometimes it's through separate passageways. Whenever we move them, and they always move in opposite directions, it's 3-to-2. If you look on the periodic table, sodium, which has a lower atomic number, is smaller. So if you're roughly, if you want to think of it that way, there's 3 sodium size-wise would be the equivalent of 2 potassium size-wise. If you want to think of it in that way, which I think is it may not be accurate, but it may be a little bit easier way to remember that 3-to-2 relationship. So here's what happens that are there. The sodium-potassium pump works as an antiporter. So as the sodium is being pumped out, it's basically optimizing the energy to pull the potassium back in. And it maintains that gradient, that natural gradient, more sodium's on the outside, more potassium's on the inside. And because of the interplay between them and the number of passageways, you get minus 70 as the end product that's there. And these are not easy to understand, but what I think they show you is here, with the input of energy, you bring 3 sodiums and spit them back out, and 2 potassiums and bring them back in. Okay? And that's what they're trying to demonstrate here with the advent of 8. So you can see here, okay, you have 3 spots, 3 spaces for the sodium and 2 for the potassium. And that's how that pump works. The pump, when you hear about people with chronic fatigue syndromes. Those, they've studied the sodium potassium pump and how it works. There's a variety of things, dysfunctions in that pump, okay, that are genetically based, are very, very problematic. So it's been studied very, very well. And so that's why I think it's really important to look at that. The secondary act of transport, okay, uses again that gradient or the force of products moving in or being pushed back out. It's almost like a wave going in, bringing stuff. If you're sitting on the seashore, all the shells and debris that comes in along with the water, they're being or transported or simported. And if you're at the ocean, particularly in the Atlantic, you have that undertow. It hits the shore and it pushes back out. We see that a lot biologically. What'll happen? The force strikes something and it's repelled in the opposite direction. That's sort of anti-porting. Kind of why your feet always get covered by sand at the shore. The Atlantic has a pretty substantial undertow, where the Pacific not so much. Just the nature of the force. Those oceans. Let's see. Okay. So low sodium concentration is maintained inside the cell by the pump. Sodium drags other things with it. Again, simporting it. And these are a variety of things. Okay. Sodium is very interesting. And again, we see that particularly in the urine, okay, with being able to move things into the cell, okay, that is there to be able to retain those sugars. And you'll see in digestion, we see it bringing things in to be metabolized. So sodium becomes a significant player. You don't really begin to look at this until digestive and urinary physiology, depending on the degree of detail, whoever your instructor would be in that particular course. By the way, at this point, I'm not going to have an AP2 lecture. Unless they need me. Hopefully not. Trying to work less, not more. So when you're done with me after this, you don't want to see me again. See, at least one person could go, oh no, that can't be true. Thanks. And I was in a good mood after yesterday. No team in the history of football wins more ugly games than this version of the Steelers, this last 20 years, the Steelers. They win ugly. Oh, ugly. Everything else requiring energy is vesicular transport. The last part, and we really need to spend more time than I have allotted for this, is we have to spend energy to open and close the membranes. Membranes are like that. You have basically two ways that it's done. Something called endocytosis, bringing things in, and endocytosis is really divided into phagocytosis. If you want to get technical, phago for eating, solids, bulk transport, or liquids, bulk transport, or penocytosis. Receptor-mediated endocytosis is very specific, even though there are receptors. Typically, there are proteins that act as receptors in almost all of these things. When we get to receptor-mediated endocytosis, there is a genetic basis, and it plays a really pivotal role in people who have problems with quote-unquote high cholesterol or lipidemias that I do have to talk to you about. And when we spit it out, we exocytosis, it exits the cell. Endo for entering, exit. There are a lot of areas where things undergo a process called transcytosis. They're brought into the cell, protected by membrane, and then leave the cell without ever having been interacted with. We see this in the digestive tract. We see this in the urinary tract. So transcytosis means just transiting. But other than that, anything that we bring into the cell, and this is a critical piece because this is the way your immune system works. It swallows something up. Your body does not know if it's going to be a nutrient or a problem. When we eat something, food's not sterile. Okay? When it's absorbed, the potential for toxins, the potential for bacteria and viruses is still there. So any one of these particles that comes in by endocytosis with very, very limited exceptions, bonds with another intracellular vesicle. When they say vesicle, it's a membrane surround something. Anything is a vesicle that has membrane around it. And this vesicle is called a lysosome. Okay, and the lysosome is filled with enzymes for digestion and defense. If it's good stuff, okay, it digests it. If it's bad stuff, okay, it destroys it. And effectively, what eventually is spit out is the waste material. So it's waste product from foods, which you're always going to have, that have to be removed and from the cell and spit out and eventually processed by your body and somehow gotten rid of. Or by the same token, if it's viruses or bacteria or toxins, they have to be destroyed and undergo the same process. So you have a lot going on every time you bring something into the cell. And we talk about trafficking, again, we sometimes have to move it by vesicles. Why do we contain it in a vesicle? If we're making something in the cell that we're going to export, the interior of the cell can damage it. We protect it with membrane. If we're bringing something in, it's potentially harmful. We protect it with membrane. If it's a nutrient, so it won't be destroyed, we protect it in membrane. That's the whole idea, and we traffic control those. So these are vesicles that have protein coats, usually involving receptors. That's what I mean, that receptor mediated is a little bit, I try to give it a more specific content. As you can see here, the bad guys can hijack that. HIV is notorious for hijacking that system. It actually is able to fuse to and be brought in. It's almost like a false flag operation in the military. Okay, effectively, it's being grabbed onto by one of our white blood cells and poisons the single most important white blood cell line in our body called helper T cells. And you'll get into that. We talk about that a lot in micro. So once the vesicle is pulled inside, it can fuse or it can just go through. And so effectively, these are important terms going forward, because understand when it comes to processing, this is what cells do. White blood cells gobble things up. They constantly are on patrol. And our immune system has basically tagged, immobilized, neutralized bad guys. And basically white blood cells go along and go, gobble it up and destroy it. That's the way they do. So anything that gets brought in by that method, by endocytosis or pinocytosis, yes, the proteins get pulled back and they get put back into the outer membrane. Now you have this vesicle with stuff in it. That stuff fuses with the lysosome. The lysosome has enzymes for digestion and defense. You're going to see there's other players that have a very, very similar role as well when we get to talk about something called a peroxisome that plays a defensive role. And so that collectively, you might call that collectively an endosome. There are names that are associated with that. And yet sometimes we're just moving it right back out and spitting it out. That would be an example of transcytosis, going from in your digestive tract and then spitting it out into your bloodstream directly. Most of the time it's interacted with, and what effectively gets spit out is the debris. It isn't necessarily the original material. That's kind of how this whole process works. So you're going to have to become very familiar with all those events of endocytosis. It brings things in. They are almost always processed. As you can see, you can go through these. Okay, the uncoated vesicle fuses. It's called an endosome, as you can see, and it can fuse with the lysosome for digestion, or it can basically deliver its contents to the plasma membrane if it's not going to be interacted with, and this is how they're spit out for transcytosis. So it works in both those different ways. By definition, when we eat, it's phagocytosis. Okay. It's phagocytosis or cell eating. We call it a phagosome. And really, we just the term, same thing for pinocytosis. We still call it a phagosome. And again, they move around, as you will begin to see, and we'll look at it next time. You're going to have tiny little things called that are made by microfilaments that are able to push on the membrane because it's flexible and create what appears to be tiny feet we call pseudopods or false feet that allow it to be engulfed. We'll look at that next time. Thank you very much. Have a great